Hi, Al Williams with HACKADAY here. I'm always looking for a simple CPU that I can use to work with students, and the other day I found a 16-bit Risc CPU on a website, oddly enough, called fpgaforstudent.com. And it looked kind of attractive. It was fairly small overall, and each piece of it was pretty small and understandable. The only problem is when I started looking at it, it had a few things that were kind of documented unusually or lightly, and there was a missing file. I recreated the file, and I kind of ran through and wanted to look at it in simulation to see how it worked. And you can find a lot more details about what I found out looking into it on the post. But I wanted to show you how I used this EDAPlayground tool, which is a free web-based tool, to do the simulation and how to interpret the results. I did log in. It's free to get a login. I think you could have probably done all this without logging in if it offends you to get a user account, but it is free to get a user account. There are a few tools that you cannot use if you're not logged in, but I don't think we're using any of them. And if you look at the setup here, I've got system Verilog as the design language. So you can do other things, right? You can do VHDL or other things like that, but we're just going to use Verilog. I didn't need any of the verification libraries. I picked Icarus Verilog, which is a free tool. You could actually just download this if you didn't want to use EDAPlayground. It's not quite as convenient, but you could do that. And then there's a lot of other tools you can use here, including some pretty expensive commercial tools. Although to use those, I'm pretty sure you do have to be logged in. But there's a bunch of free options as well. And then most importantly, I've got this open EP wave after run. That's how we're going to see the results. I pretty much assume that you know some Verilog before you'd go tackle a CPU design, but just to give you a quick overview of how this is structured, normally when you write Verilog code, you're targeting an FPGA, and you'll break it into two pieces for simulation. All these pieces over here on the right, all these different files that you see here, are generally what you're going to build that would go to the FPGA. Now, the way the thing came off the website, there's a couple of things in here that really wouldn't synthesize well. There's some initialization that's really pretty much just for simulation, and that includes some data files that I'll show you in a minute that wouldn't actually synthesize down to FPGA. So if you wanted to really put this on an FPGA board, it would be a little extra work. Nothing too hard, but it would be extra. But in theory, this is all the stuff that would go over to the FPGA, and then you usually have a test bench which just drives that device, tests it. A real-life test bench will usually collect some data and either store it somewhere, or it will test and say, well, that should be a 5. It is a 5, that's a pass, or it's not a 5, that's a fail. This one's pretty simplistic. It just lets it run, and you have to visually go inspect the data, which I'll show you how to do that in a minute. There's only one file here, but you could add more by clicking that plus button. It expects that file to be testbench.sv, and you really can't change that. Same thing here. On this side, there's a design.sv. You've got to have that file, and you can add up to 10 files on both sides. The tool is a little peculiar. This isn't a problem with the code from the website. It's a I won't say problem, but it's a peculiarity of EDAPlayground that it really only looks at this file and this file. So if you want to get these other files in here, you have to include them, which I did right here. The problem is each one of them has a time scale at the top of it, which is normal. That should be there. So because we've included them all into one big giant file, we're going to get some warnings that say, well, there's a time scale, but hey, you gave me another one, you gave me another one, you gave me another one. And it's harmless. It's a warning. Don't let it alarm you. One of the things I did like about this, though, is the files are pretty straightforward. They don't do a whole lot in any particular file. And then taken all together, though, it's a reasonable CPU. So you can see the main file here. It just instantiates a data path, which is where you get all the resources, the arithmetic logic unit or ALU, memory, registers, things like that, and a control unit that orchestrates all that. And that's it. Pretty simple. The data path, of course, is in another file. Now that file is a little more complicated. That may be the most complicated one. but really it's not doing a lot. It's just creating a bunch of things and wiring them together. And those things are like the ALU, for example. We'll look at the ALU. It's very simple. Piece of combinatorial logic says if you get this opcode, do an add. If you get this opcode, do a subtract. So pretty simple to work through that and kind of understand what it's doing. The control unit is a little verbose, but it also is pretty simple. It's long just because it's got a lot of duplicate cases that could have been condensed. But, you know, it says, well, if you get this opcode, here's all the control signals you need to assert. And you'll see in the post there's a table that explains why all those control signals are being asserted, and it kind of controls the flow of data through the CPU. So there's quite a few cases there, but it's really simple to understand. It's just for each opcode, turn on some signals and turn off some other signals. There's two data files here, and again, those wouldn't synthesize. There is a data file, and that's the memory, the RAM memory, and that's just in binary. So the RAM memory is going to get loaded with that. And there's also a program. Well, they included a program with the original source. It's fairly long, and it tests a lot of different instructions. And that's good for testing, but if you're just trying to run this and understand it, it's kind of hard to trace the program flow. So I wrote a much simpler program. You know, I essentially load a 1 into a register, load 1 into a different register. I add the two registers together into a third register, so that gives me 2 in that register. I wind up saving that into memory, loading it back so that I wind up with the 2 again to work on the next loop. And then I do a jump, so I'll add 1 again, so I'll get 3, and I'll write that to memory, and then I'll get 4, and I'll write that to memory. The jump is really peculiar because you're going to see you want to jump back to location 4 or byte 8, and it's kind of strange. You've got to actually jump to the word address above where you want to go because it's always fetching ahead. So the offset on that jump looks like it's a 2, but really it's going to jump back to there. And that was a little tricky to figure out. Like I say, the documentation on this is a little sparse. So you really have to kind of read the code or go through this kind of exercise to see how everything works. And then the test bench is very simple. There's a dump file. I had to add that in there. That's where EDAPlayground is expecting to find the data, and it just generates a clock and waits for everything to finish. So let's go ahead and do a run. And we got a pop-up. And if this is already up, it won't pop up. You'll think, well, nothing happened. It's done, but nothing happened. You'll have to go bring this up manually. I just had it closed, so it did pop up automatically. And it says, well, you need to use the Get Signals button to figure out what's going on. Now, normally when I do a test bench, I would have all the signals brought up here that I was interested in looking at. But here we don't do that. There's just a clock. So I'm going to go, and it adds things in the way that in the order that you put them in, so it's hard to grab everything at one time because I want them in a particular order. I'm going to get the program counter, and you can see down here there's the program counter has showed up. I want the instruction that it's executing. I'm going to go to the register files, and I'm going to go read address 1, read data 1. I'll go read address 2, read data 2, and I'll go to the write address and the write data and the write enable. And then I'll go to the data memory and I'll say, let's look at the address, the read data, the write data, and the write enable. And I think that should be enough to let us see what's going on. So the first thing to notice, the program counter is running through, and it goes through and does the jumps like we expect. So it's running through the loop. We see the instructions we expect. And if we look at the memory writes, you'll see that it writes 2, and then it writes 3, and then it writes 4. So the program did what we expected it to do. And of course, you could obviously go probe into these signals more if you wanted to. You could write more programs and see what happens. But, you know, for a little bit of effort, you got a 16-bit Risc CPU. It's not pipelined or anything. That would be the proverbial exercise for the reader. But it's manageable. The documentation, like I say, could have been a little better, but if you look at the post, I've kind of elaborated on some of the things that I thought were tricky about it. And it might not be a bad project for somebody wanting to start out and take a look at CPU design in Verilog. Now, there's a lot more you can do, obviously, and there's a lot more complicated examples you can look at, but this would be one thing interesting to get you started. Anyway, hope you enjoyed that, and thanks for watching.